You've seen puzzles like this on social media. What the idea is you'll be a genius if you could figure this out. And the assumption is that if water's coming out of this tap, it'll fill up this tank until it gets to the height of that pipe and then start filling up this tank, and this one will go no higher, and then start filling up tank C when it gets to be this full. And if you follow that along, you'll see that it would go to tank D and then to tank G. But wait a minute, tank D is a blocked pipe, so no flow there. So the simplest solution is if water's flowing in here and it only gets up to that pipe and then it goes to tank B, then you just need to follow the pipes and note the blockages. But that would only work if we put the water in really slowly, because for that to happen, the water would have to be coming into the tank more slowly than it could possibly flow out of the pipe, so that as the water pours in here, it all flows out there. If we're interested in doing this quickly, and we usually are in an engineering environment, we'd like to know what happens if we have higher flow rates. If we make the flow rate really high, then this tank A is going to fill up first, and the overflow to tank B is going to be smaller than what's coming in through the tap, and as a result, tank A will overflow first, and B will only be partway full. So if we want to understand the dynamics of systems like this, we really need to look at differential equation models, because those tell us how quickly things are changing with time. So if we consider conservation on tank A, the rate at which tank A is filling up depends on the difference between how much water is coming in from the tap and how much water is going out through that pipe. And we could specify how much water is coming in from the tap, either a small flow or a large flow, but we'll need to calculate how much water is going out through pipe A, or this pipe from tank A to tank B, based on knowledge of how full the tank is and how much friction there's going to be in that pipe. Now that's knowledge you don't have yet. You'll get that in a fluid mechanics course. But I'm going to build that knowledge right down here so that we can use it in our simulation. So if we have laminar, well-organized flow in the tube, then the flow rate depends on the elevation difference and the friction in the tube, which is what I just said. And it's also going to depend then on how long the tube is, because the longer the tube is, the more friction it's going to have, and the higher the viscosity, the more friction it's going to have. And you'll run into this relationship later on in Mech 241. Now, by doing this balance between friction and elevation, we're ignoring the forces that go into accelerating the fluid. And it gets more complicated if we add that in later. But let's try building it into a function with just the friction. So we'll do a 1 centimeter tube, and I'll define this function, which is flow rate, as a function of elevation, so how high the water is above the tube, the length of the tube, and the diameter of the tube. The viscosity of water, 1 times 10 to the minus 6. Gravity is 9.806. And then I can just use that formula I had up here for Q to get pi g over 128 times nu times d to the 4th over L times h. And if I run those, I get that the flow through that 1 centimeter tube, 1 meter long with 1 meter of elevation change, would be 0.0024 cubic meters per second, or 2.4 liters per second. Reasonableness check, 0.00033 cubic meters per second, is 1/3 of a liter per second, or about 1 beverage can. So that seems like a pretty high flow to be coming out of that small tube. And what's going on there is that for this short tube, the friction isn't particularly high. So we have to take into account the elevation needed to accelerate the fluid to the speed that it's traveling. Because if it just fell 1 meter, it wouldn't be going as fast. So this function gets a little ugly, and the numerics of it are a little bit difficult. But you'll be able to manage that a little better after you do the Math 272 course. Again, I'm just building this one so that we've got something to do some dynamic simulation with. So I'm going to change the definition of this HLD function. I'm going to start off by saying, well, which direction is the elevation difference in? Because if the elevation difference is negative, then I'll just do it as if it's positive and change the sign at the end. If it's really close to 0, I'm just going to return 0 because that stabilizes my calculations. I'm going to make a first guess by just ignoring the friction. How fast would the flow be moving? How high would the velocity in the tube be if the liquid just fell that distance? I'm going to have two numbers, delta and n, to help me keep track as I iterate towards a solution. And delta is going to be a measure of how much things have changed in the iteration. So it'll start off big, and I'm going to try and make it small. And n is just going to be the count. So in this function, I'm saying that while the delta is larger than a small number, and the n is less than 1,000, so don't keep iterating more than 1,000 times, we're going to improve the estimate. So what elevation would be required to overcome the friction if we had the velocity equal to just the falling velocity? And we can calculate that elevation from basically the same relationship we had up here, this one, but expressed in velocity, because velocity is flow rate divided by cross-sectional area. So we can calculate the head loss due to the friction that results in that tube. And now we're going to try to move slowly towards the right answer to avoid some numerical instabilities. So the elevation difference that's available to accelerate the flow is the maximum of either the elevation, the original elevation minus the head loss due to friction, or some small value of the elevation. So this is saying that we're going to take a slow step. We're going to use 0.1 instead of 1. We're only going to take a small step towards it, and that's going to improve the stability. It'll take more iterations, but we can watch the convergence and see what happens. So we'll then calculate V as the square root of 2 times G times the elevation that was available without the friction. So instead of up here where we used the whole thing, we'll use a reduced value to allow for the friction. We'll calculate delta as the absolute value of what the velocity was and what the new velocity is divided by its magnitude, and we'll increment the count there. And then we'll calculate the flow rate as the area, pi d squared over 4, times the velocity. And finally, we'll return the flow rate and we'll multiply it by the sign that the original elevation was, just to make sure it's going in the right direction. So let's try that, see what comes out. So let's try running it. We'll use the values down here that we used before when we got that 2.5 liter result. And I'll run. And it starts off by saying that the flow velocity would be about 4.4 meters per second if we just had acceleration going on. And the elevation component that it would require to overcome the friction is just a small fraction of the 1 meter of elevation that was available. So we wind up with a flow rate of about a velocity of about 4.39 and a flow rate of about 0.000345. So something way closer to the magnitude of our beverage can. So let's try that again with a negative value. If we got our signs right, it's just going to come out and say the flow is going in the opposite direction. And that worked out okay. So we've got our flow rate here. We can calculate it, and we can put in any values we want here. So for example, if the tube was longer, we would see that the flow is still about the same. There's still not a lot of effect due to friction there. Came down a little bit. If the tube was considerably longer, it's still not a major component coming from friction. It's reduced only by about 10% here. So that's kind of interesting. Now let's try and see what happens if we change the diameter. Let's go down to 0.05 of the as a diameter, so half as big. The flow went down by orders of magnitude, and we have much more of the elevation coming in as a result of friction. It takes more iterations to get to our solution, and we do finally get to a value. So now we've got this flow rate function. It's kind of complicated. I don't think I could take derivatives of Q. So let's just pack that one away, know that we've got a function that tells us about flow rate, and let's do some reasonableness check. We got down to a value that was closer to our 1 can per second, and we tested on a range of values, so that makes a certain amount of sense. So now let's try it over a whole range of different elevation differences. So here I'm going to take 140 points. I'm going to have a linear space in elevation between -5 and +5 meters. And I'm going to calculate the flow rates for that. So I'm going to make a copy of the elevation change and then fill it in this for loop with flow rates. So I can calculate the flow rate from the function for a whole lot of different elevations without needing to know what the actual function is. And that's why we defined this function before. Then I can plot it out. So if I do that, whoops, it's printing out a whole lot of numbers. I will go up here, and I don't need to watch the convergence of all of those 140 calculations. So I'm going to redefine that function. And you see now it comes out and it just prints the answer. So now I'll go down here and I'll run this one again. And when it runs through, I see that I've got this fairly complicated S-shaped curve. Now we could get an analytical version of that, but I really want to use this as an example so that we can figure out how to do the system dynamics. So this is all stuff that we're going to take as a given. We've got this Q function. Now let's go use it.